A dopo.
Okay, dear colleagues, ladies and gentlemen, thank you very much for attending the 5th seminar of the Geo-energy Webinar Series 2021. It's a real pleasure to me to introduce today Chiara Boschi, which is a researcher, a scientist at the Institute of Geoscience and Research at the National Research Center. Today we will go across different topics of the various we have been crossing in the last 4 weeks across the geo-storage, which is the importance of the mineral carbonation into the geo-storage capture of the CO2. As I usually say, this is a seminar which is active as well on the YouTube, on streaming live, which link has been advertised already. So any one of you that is willing to download the presentation or see the presentation across the YouTube channel, feel free to connect there. It is starting lively as well in this moment. Before I give the word to Chiara Boschi, just give me a short introduction of the speaker today. Chiara Boschi, she's an expert of CO2 storage. She did a PhD at the ETH of Zurich, where she's been working a lot on oceanic serpentinite, and then she came back in Italy and she started to work a lot on
Ora si registrerà la conferenza.
Becoming an expert on the aspect which relate to mineral carbonation, which has been also a scientific consultant for various national institutions. At the moment, she is leading as well the stable isotope laboratory within this institution. And she is now, as I said, working since a while on the subject that she will introduce to us in a short time. I remember after the 30-40 minutes of the talk, there will be time for open question, which you will be free to ask across the chat or directly asking to the speaker. And therefore, I will see you in half an hour, and I leave the word to Chiara Boschi. Thank you very much.
Thank you, David. Thank you to everyone to come at this meeting. I'm Chiara Boschi, and I'm working on CO2 capture and storage by mineral carbonation since several years at the Institute of Geoscience and Earth Resources of CNR. Today, I would like to convince you that mineral carbonation can be another option of CCS. I start, as David told us, I start working on CCS many years now, and I start with the feeling that the CCS is something that is a technology that is nice to have, but by the time the CCS is become necessary and now inevitable. I start with the diagram that all of you knows about global fossil CO2 emission is increasing, and now in 18, it's reached 36 gigaton per year, the global fossil CO2 emission. And is something, the global concentration of atmospheric CO2 are higher than any other time in human history. From pre-industrial time, baseline, we are now at about 409 ppm in 2019. This is something that pushed IPCC, that is International Panel on Climate Change, to write down a global warming report for taking the global warming at 1.5 degree. And what they try to figure out is a different mitigation strategy that we achieve, with which when we can achieve 1.5 by 2100. So all pathways use carbon dioxide removal, but only P1 exclude CCS. The other three scenarios mix a number of strategies. In this scenario, I don't want to go in detail, but this scenario takes into account all the possible chances. It's mean renewable energy, it's mean land use, afforestation, or change in land use, or decrease of fossil fuel utilization to zero, and increase efficiency, and all the mixing chance that we can have. And also each scenario change from one to another depending on the variable. So how much we want to decrease, how much we want to increase each type of strategy. But in P2, P3, and P4 scenarios, CCS take a very fundamental role. But where we are now, today, only 260 million tons of CO2 has been stored with CCS technology. So it's this number is cumulative. So all the CCS facilities store up to now only this amount of million of CO2. But what IPCC told us that we need to store 350 to 1,200 gigaton of CO2 until 2100 in cumulative way. So this is a cumulative number that are, it's mean 4 to 15 gigaton per year. To achieve a multi-gigaton annual CO2 storage rate, the world will need to characterize, appraise, and develop thousands of individual storage sites. Another report gives us another idea of what we need. We need 30 to 60 storage sites each year until 2050. So at the moment, there are 19 CCS facilities in the world in operation, 4 in construction, 28 in a stage of the development. And they are mainly in America, and the 24 are in America, 12 in Europe, 12 in Asia, 3 in Middle East region. And in Europe, there are very concentrated, the CCS facility are concentrated in North Europe, mainly in Norway, that historically start CCS facility. And historically, for example, when I told historically, because Leitner is one of the older CCS storage sites. But other CCS facilities are in UK, and some in Netherlands, 1 or 2 in Belgium, but very few. And as you can see, none in Italy. Okay. So most of the operational large-scale CCS projects are based on enhanced oil recovery. It's a whole technique that have been used since several years from the energy company to increase the amount of oil that we can extract for an oil well or an oil semi-exhausted well. So, but this is something that you can apply mainly in sedimentary basin. And in sedimentary basin, you have to put, this is oil recovery sketch, and you inject your CO2 in your basin or in your layer, rock layer, and there are 4 phases of trapping. The first trapping is structural trapping. After the CO2 is trapped in the residual pore, that is called residual trapping. After again, the finally CO2 is solubilized in the fluid that is inside this pore, and only at the end, in very small part, we have a mineral trapping. For sedimentary basin, for sedimentary rock, mineral trapping is not fundamental because there are not enough rock minerals that can be reactive to make a mineral trapping, to make a process that is called carbonation. We need to have this kind of reaction and silicate bound divalent method or to produce the reaction of carbonate formation. Another key challenge for the CCS in sedimentary basin that other presenter already give an idea is the fact that one of the main problem of this kind of traditional CCS, if we can speak about traditional, is that the problem of leakage. Leakage is always the problem in this kind of technology. CO2 will remain in the gaseous or liquid or supercritical phase long term. And if it's not adequately stored, it will tend to migrate back to surface. This is the reason because in 19, a colleague from America, Siegfried, wrote down a paper in Nature, a very short communication, and tries to suggest another solution. The solution would be use a different type of rocks. That's exactly the mineral carbonation. So the mineral carbonation is based on injection CO2, but not in sedimentary rock, but in basalts or in ultramafic rocks. In this way, we want to accelerate a natural process. In nature, we already have this kind of process that is called carbonation or weathering of silicate rocks. And we have each year vast storage of carbon in rocks that remain over 1 million of years. So with this approach, the capture carbon is stored through its injection into reactive rocks, such mafic or ultramafic lithology, that contain high concentration of divalent cations, so calcium, magnesium, iron, for example, for rapid mineralization in presence of fluid rich on CO2 to form calcite, magnesium, and siderite. This is more rare, that are stable over geological time. But these are the normal reactions that we have for carbonation. So serpentine plus CO2 give magnesite plus silica plus H2A and energy. And the same with olivine. Olivine plus CO2, magnesite, silica, and energy. These are reactions that are exothermic, are spontaneous, happen in nature, and we can observe in nature, where we have a deposit of magnesite that are called natural analog of mineral sequestration. So if we go in more detail, what happened, that the water that is saturated in CO2 become more acidic. The pH can range from 3 to 5, and this kind of water can easily attach mafic, ultramafic rocks with the dissolution of silicate minerals. And the silicate mineral, serpentine, olivine, or also oxide, brucite, it's another type of mineral that easily react in presence of CO2-rich fluid. And with the dissolution and the release of calcium, magnesium, and iron. These easily form carbonate like calcite, magnesite, and rarely siderite. But the degree to which they release cation for minerals depends on the element, pH, and temperature. For example, calcium really reacts with CO2 at the temperature below 300 degrees. Magnesium precipitate the carbonate, magnesite, and dolomite at temperature lower, so above 65 degrees, but lower than 150 degrees. But at lower temperature, at the lowest temperature that we can have this kind of process, we have the formation of another type of mineral. They are hydrate carbonate that is called hydromagnesite. You see the water inside, the structure of the mineral, the dippingite and esconite can form. Another big deal of this process is the pore and the fracture evolution. Pore and fracture provide pathway for migrating fluid that access to mineral surface that contribute cation to the mineralization space for the carbonate precipitation. The main risk that what happened that the carbonate associated secondary mineral precipitate, because they have a larger volume than the primary assemblage, mineral assemblage, they can clog flow pathway. And this is something that cannot make the chance to the reaction to go to the completion. But what we see in nature, in the natural analog, so in the magnesite deposit that we are studying, that this volume expansion, for example, for a serpentinite is up to 20% of volume expansion during precipitation, crack the rock and open new fracture. And in this case, we speak about hydrofracturing. This is a process that very typically characterizes all the magnesite deposits that we are studying. And this may promote subsurface carbonation. These are two examples of hydrofracturing when there are clasts that are the precipitate in the first stage of the carbonation after a second stage after the hydrofracturing. This kind of rock are spread out everywhere in the world. This is a map showing magnesium rich ultramafic rocks, basalt, anorthite. This is a map made by a review of SANA in 2014. But there are many more of this kind of outcrop, and this can suggest that mineral carbonation provide an attractive alternative or addition to the more common sedimentary injection CCS technique. First of all, it offers an expanded geographic range of onshore and offshore storage. For example, if we include large flood basalt province, large massive of mantle peridotite, ophiolite, serpentinite, oceanic ridge. If we take into account only the basalt, this is the typical map. That this is another paper, that very nice paper from the Carfix team that come in the Nature last year. And this is a map showing the oceanic ridge and the igneous plateau continental flood basalt. And they made a roughly estimate of what we can store, take into account this kind of rocks, and the storage capacity of the oceanic ridge. Only the oceanic ridge is an order of magnitude larger than the amount of CO2 that will be derived from the burning of all fossil fuel. So we are speaking about a very alternative, attractive possibility of apply this kind of technology. This technology has been tested. First of all, the most important project of mineral CCS is called Carfix. Carfix is a project that is funded by UA. It's a Horizon 2020, is a Horizon project, FP7 project, I don't remember which one, that is started in 2012 in the southwest of Iceland. And the idea below the project was to attach a geothermal plant to CCS. So the idea was, this is the scheme, to take out the geothermal gas, condensate the geothermal gas, purify this gas, and inject. In the second stage of the project, that is called Carfix 2, they add also and capture from air. This because usually typically the geothermal fluid, the geothermal residual gas of the Icelandic geothermal field is poor in CO2. This increases the amount of CO2 that we can store in the underground basalts. And for Carfix 1, this is just a pilot small project. They store 230 tons of poor CO2 and a mix of CO2 H2 gas mix. And at the depth of 500 meters into basaltic rocks at a very low temperature, 20 to 50 degrees. The critical point here was the amount of water, because they tried to test an innovative type of trapping. They wanted, this is a sketch. On the left part is the 4 types of trapping of CO2 that usually we have in sedimentary basins: structural, residual, solubility trapping, mineral trapping. Here is the year of injection, and this is the trapping contribution. As I told before, the mineral trapping for sedimentary basin is a minor component. And but this arrow gives you the safety of the storage technology. If we go from structural to mineral trapping, we have an increasing of storage security. In Carfix, first of all, they inject CO2 already solubilized in water. And in this case, they avoid the first 2 trapping stage. So they inject, and the CO2 was already solubilized in the water, and the mineral trapping come very, very soon because they use basalt instead of sedimentary rocks. They quantify using reactive and non-reactive tracer isotope, which will be that in only 2 years they can trap and they can mineralize CO2 into the carbonate. So what next? The Carfix want to go further, and they want to, up to now, they store 33% of the CO2 emission from the power plant, but they want to go to the 90% before 2030. And they want to build up a new new injection, new well that start to operate this year. And start to operate in another project. This project is called Gecko Project. And this is where we have the injection, and in the next one there will be very surrounding area. There is a 2 injection well. The Gecko Project, I'm very happy to be involved in this project. This is the picture this is the picture where we went to the injection plant for the kickoff of the meeting, the Gecko meeting that started in 2018. I coordinate the Italian team for the Gecko Project, together with a lot of colleagues of my institute. This is the banner of the Gecko Project, pushing the limit of carbon capture and storage underground. It's a big consortium. It's a consortium of 18 partners. The project will end in 2 years, or 1 year and a half, sorry, and with 16 million of grant. The goal are the similar goal of CarbFix, to lower emission from geothermal power plant by capturing them from either reuse or storage. So here we made an additional goal, reduce just to, for example, commercial use of CO2, because one of the goals was to purify in the best way the CO2 that come out from the geothermal power plant for commercial use. Or another chance is to make ex situ mineral sequestration, not only injection of CO2, but to utilize, to reuse the CO2 purified in a plant build up ad hoc very close to the meter, and to produce the same reaction of carbonation, but in a pilot plant. To demonstrate the cost competitiveness and the developed gas capture injection method, we made also in this project an economic analysis of gas capture, injection, and monitoring at each field site. The site were 4 in Turkey, Italy, Germany, and Iceland, where we have CarbFix. And what we are doing, the project is still ongoing, and we are studying. We start before Gecko Project, but we are studying the chance to apply mineral CCS in Tuscany. Why Tuscany? Tuscany is very an ideal place where to apply CCS. It's a geothermal place, first of all, as Iceland. There is Larderello geothermal field that's very famous everywhere. And there are a lot of philitic rocks, not only basalts, but serpentinite and basalts, gabbro, that outcrop for 230 kilometers square kilometer. And the buried ophiolite are like larger volume than the exposed one. Another very characteristic of this place, my region, is that there are a lot of natural analog. The natural analog is the magnesite deposit, exactly what I was speaking before. So this type of carbonation reaction happens in nature. And here there are a lot of deposits already that already store spontaneously, almost 2 per 10 to 6 tons of CO2 through time. So we select a number of sites where we went to study on geological, geochemistry, petrography, everything to characterize our, first of all, the magnesite deposit. Why we want to characterize the natural analog? Because give us the idea how to accelerate the process on industrial level, where we can have the maximum efficiency of the process, what are the main parameters to speed up or to increase or decrease. So we want to know exactly what happened in nature. So, and there are 2 end members of this kind of natural occurrence. One is high temperature and there are magnesite deposit hosted in serpentinite asburgite. The other end member is very low temperature and is with formation of hydromagnesite and hosted in serpentinite dunite. This is the map with all the occurrence in Tuscany. And going to the high temperature example, this is, for example, I come from Malintrata magnesite deposit. We published already 2 papers on these deposits, and it's characterized by several carbonate silica veins that are hosted in plurikilometric masses of silicified carbonate and argillified serpentinite of the Liguria unit. The important things here, first of all, the reaction went to completion perfectly. No, we don't have any evidence of the primary mineral assemblage. All the serpentinite is transformed in a new mineral assemblage, and the carbonate vein occur with an apenninic orientation. So it seems to be that they are formed along an active fault. These are example of the deposits, and this I make some picture. This is the vein, the big vein. This is the hydrofracture deposits, and this is like, for example, an example of the serpentinite that is surrounded by different generation of first magnesite, and in green a dolomite, and at the end opal come and deposits. It seems to be a very late stage opal. Again, this is another type of rocks, very nice. That are, these rocks have been used in the Renaissance time to build up the table in the Medici area time, the Medici time. So this is the reaction again, serpentine plus CO2 give magnesite, silica, H2, and energy. In this case, this is a sketch. This is a paper that we submit very few days ago. What happened in this system? There is this weak fault, weak layer where the fluid comes through and interact with serpentine, completely dissolve the serpentine and deposits magnesite and dolomite. This is something that happened when this kind of rocks were buried at least at 1 kilometer depth and a temperature of about 100 degrees. And it was something that happened, we guessed, we are trying to date these rocks, but our impression that was during the Miocene, Pliocene time. And the sketch that we try to, in this sketch, we try to figure out how it happened. And from our isotopic analysis, it comes that the CO2 that formed carbonate is CO2 that come from that. It's mantle CO2 that come and follow some lines, some folds that are already active in this system. So go to the low temperature minerals, CCS analog. What we can learn from this? This is another type of deposit, completely different from the other one, because it's something that is not intensive affect the rocks. We are at Monte Castelli, still in southern Tuscany. There are the river erode, the serpentinite outcrop, and there are, you can see this whitish part of the rocks of the outcrop that are dunite. They are completely wrapped by mineral, not intensively in depth, but superficial. So it's a low temperature reaction that between meteoric water and serpentinite. This is how it appears. So it's like a coating of the rocks and not going in deep. So the rocks, if we try to keep this rock and open these rocks, there are still the mineralogical paragenesis characterized of the serpentinite. So these are other type of example. These are very end rocks. So this is very few thin coating made by this mineral that are hydromagnesite, nesconite, dipingite. You see this rounded rosette or spherules that form on. It's a very ongoing process. It's something that happens in few days. So if you go, each time that we go and to sample this kind of rock, there is new occurrence of this type of minerals. But in this case, the reaction is a reaction that affects not serpentine, but brucite. Brucite is another mineral typical of serpentinite, especially in dunite. And brucite easily dissolves in presence of meteoric water rich in CO2, forming the hydrate carbonate. This is exactly what we are speaking about, the ex-situ mineral sequestration. This kind of reactions, low temperature, that can apply ex situ, not in deep. And what we have, there is a number of chance to have the ex situ mineral process. Last time at the seminar, someone asked about ex situ mineral carbonation. It's a word not only made by, studied by geologists, but engineers or other that try to convert not only mine or made of ophiolite, but also alkaline waste residual or steel slag in presence of CO2 to form carbonate. This is because we need, the only things that we need is cations, so calcium and magnesium that we can recover also from the alkaline waste residue. This is just a scheme of all the large world of ex situ mineral carbonation. There are very hundreds of studies and papers on this kind of carbonation. That is something that's very industrial sector. What we are studying, just a part of it, it's more the geological part, and to try to figure out which one are the best conditions to reproduce for industrial use. So in summary, this part of Gecko and the natural analog study, it's an example of the possibility of in situ and ex situ process that we can reproduce. The first one is efficient because all the rocks are completely transformed. And the magnesite deposit, it's huge and cover most of the part of the ophiolite in Tuscany are characterized by the occurrence of magnesite. The second, it's ongoing process. It's an interaction between meteoric water, CO2 that come from the soil, and with the surface of the rocks. This is something that can be, for example, applied in the abandoned mine, or something just also to recover asbestos. This is another application that we can recall with the ex situ approach. Another part of the project, we don't study not only the natural analog, but what we can apply, how we can apply this CCS. And we made a roughly estimation, as the CARFIX team did for the Mid-Atlantic Ridge, of the ophiolite occurrence in Tuscany. This is a very roughly estimation, but theoretically we can sequester up to 100 gigaton of CO2, assuming a thickness of 500 meters. So it's equivalent to 200 years of greenhouse gases emission in Italy. So what we are trying to do, just with the help of other colleague of me, it's to find, this is our older well, explorative well or abandoned well from the Enel company. And we manage in our institute a database, and with the database we can have an idea where they are the ideal place to store, where we found the confined body of serpentinite, where we can apply in situ mineral sequestration. So to do that, we have to exclude a number of limitations. For example, we have to be away from seismic epicenter location. We have to be very far from protected natural area, and very not at the same place where we have a natural CO2 degassing that affect all the terranean coast of Italy. So this is what we are doing. We still are ongoing. We start to publish other paper on the potentiality of CO2 or mineral CCS in Tuscany. To conclude, I would like to I try to convince you that to conclude, I blocked my presentation. I don't know why. I don't know. Ah, finally. Okay, so carbon capture. Oh, no, sorry, something is wrong here. Okay. And something is blocked, but I hope. Oh, okay, maybe. So to conclude, the carbon capture and storage has a key potential to mitigate climate change and to be very efficient technology for mitigate the climate change. And it's everything is crazy now. I don't know why. Sorry, just a second. Try to. Okay, again. Okay. CO2 storage through mineral carbonation extend the applicability of carbon capture and storage by enabling storage in area previously not considered feasible. The rapid mineralization of CO2 through injection into reactive rocks formation increase storage security. And this is a very key point. Carbon mineralization in mafic, ultramafic rocks offer a global storage potential that exceeds anthropogenic emission. The method can be used for the subsurface storage of CO2 and for ex situ application. So the carbon, we have to push at all levels because we need considerable effort to accelerate the development of CO2 storage through mineral carbonation, including more widespread operation in diverse conditions. So this is the message, the take-home message I would like to give to you. And this, I very thank you. I'm sorry for the crazy slide at the end. And this is for more information. These are all the link of the Gecko Project. Thank you.
Thank you very much, Chiara. Beautiful talk, very interesting, informative subject. I will say I will open now the discussion, and therefore anyone willing to ask question, it's time now to feel free to intervene in the conversation. I see David Waltham. If you are willing to ask the question directly, thank you very much. David?
Right, sorry, having trouble working it out. I just want to know what slows this process down. I suspect that you can't inject CO2 very fast compared to the rate at which you can inject it into sedimentary rocks. Could you comment on that?
We do have a... Oh, well, I think we missed the...
I think the microphone is out. Chiara, your microphone.
We lost Chiara across the...
Il microfono.
Here you go. Now we can hear you.
I think she's speaking, but with no microphone.
We can't hear, but the microphone is over.
Chiara? Don't worry, you may have to change the microphone maybe. Can you hear? We lost the connection.
Can we ask to Chiara to close the connection and to reopen the link?
Okay. Try to wait the speaker if he can get back. Unfortunately, sometimes we do have those issues with webinar when the connection got lost. So be patient and we will be back with questions, and hopefully Chiara will be able to answer to you, David.
I look forward to
Here you
it.
go, she's back.
Okay, now?
Oh, very well. We can hear you very well now.
Sorry,
So
I don't
please,
know what's happening.
it's okay, it's happening.
Okay. So
If you can answer the questions.
the question,
by
can
David.
you? Yeah, but I lost the question. So can you give me again the question?
Okay, can you hear me?
Yeah, thank you. Sorry.
Yeah. What I'm wondering about is the injection rate. You know, if we're injecting carbon dioxide into sedimentary rocks, we can inject from one well 1 million tons in a year. I was wondering how that compares to what you can do in your approach.
You mean that it's, I think we can have the same, but of course the mineralization will take more, because if you inject a large amount of CO2, it will take much more, because and Carbfix project is very small project, pilot plant, so they inject very few amount of tons of CO2, so it's clear that the reaction go very fast. I guess that we have the similar situation that on the sedimentary basin, but the reaction time for mineral is much higher. So in sedimentary basin, the problem is that we don't have cations, we don't have silicate minerals to react. Of course, mineral trapping is a very small process. So of course, when we speak about 2 years, like in Carbfix, it's something that is compared to the amount of CO2 that has been stored. That is very few. It's in total is 200 tons of CO2.
Okay. There is Domenico Chiarella. Would you like to ask the questions you did write on the chat?
Hello. Hi, can you hear me?
Yeah.
Can you hear me?
Yeah.
Yeah.
Okay. Ciao, Chiara. Thank you very much for your talk. I have just a couple of questions. Maybe you already answered the first one. So, what is the impact of this rapid mineral carbonization on permeability? Because if we start to fill the pores, we will have difficulties to continue to inject through years. And
yeah, I just stopped before the second question. Yeah, this is true. There is a problem of permeability, especially in serpentinite, because serpentinite are very low permeability, just secondary permeability for the fracture of serpentinization itself. But at the same time, you have a hydrofracturing, because we have a volume expansion. So it's something that it's something that can enhance the permeability itself, because for example in Tuscany the hydrofracturing is an example, and all this deposit, it's along active tectonics. So one thing, of course, I don't want to inject inactive fault CO2 for sure, but hydrofracturing is a technology that has been used for all companies since several decades. So this is something that can enhance permeability. I know that this is a risk and all the problem with social acceptance, but this is the only way to increase the permeability and increase the rate of mineral precipitation. Otherwise, the stop.
Okay, so I don't know if you read the second one. It's since the minerals.
Go ahead.
have a larger volume compared to the. So when we estimate the volume, because at the end of the day, there is the project should be economically viable. Otherwise, there is no point to run it. We calculate the volume of the potential CO2 that you can inject. But since the volume it's larger, and then to which order should we downscale our volume and during our assessment? If there is an order of magnitude that you can say, and
sorry.
And the other linked question that may be also linked to your previous answer: can we control this fracking created by the minerals, and in which way they can deteriorate our reservoir integrity? Because at the end of the day, we want to keep the CO2 down there and not to release. So thank you.
So this is all the good question, and this is a question that are under study. Of course, what we know that the volume expansion, this is a calculation is made by different person. I can refer to Cipoll, it's an old paper that made a calculation of serpentinite that goes in carbonate with a 20% of volume expansion. What happened with the fracturation is something that we don't know because we don't have pilot plant in serpentinite. But this is, of course, is something that we test somewhere, someone, because otherwise we cannot have any clue or any other information. This is what happened. Of course, I will suggest that first of all, we don't have to test in active tectonic area, but in some places that are not tectonically active and not densely populated. But in some way, we have to have an idea. We did different experimental lab, but as you told before, it's very difficult to compare to the natural reaction. Also because in all the lab that we are doing, we have to accelerate the rate. And to accelerate the rate, we don't have the real condition that can have below in subsurface. So we have to accelerate because we cannot have a 10 years or 2 years long process. So it means that we have to crush the rocks, we have to add or increase temperature or add some additive or acid to increase the reaction. So it's something, for example, I think now it's 5 years ago, was like a project, a proposal project to do in Oman. Oman, for example, is a perfect way to test injection in serpentinite. It's not densely populated, it's not very, and there are a large amount of serpentinite that is made by serpentinite, the Oman classic ophiolite sequence, and there we can test. But for some political reason, at the moment we don't have the test yet. It's only a ICDP drilling to study, but not project of injection.
Okay, thank you very much.
There is another question I see on the screen. Mattia Pistone, I don't know if he is around still.
Optimal condition of storing carbon without yeah, so it's all the same. Yeah, I know Italy, it's we have ciao Mattia. Yeah, Italy, it's okay. First of all, we have a problem, public acceptance, a very huge problem. I didn't mention the problem with Gecko Project. So one of the 4 sites in Italy was very close to the outcrop that I show in Monte Castelli, Malentrata, and this site was stopped due to the problem of public acceptance. They don't allow us to go and inject CO2. It was not injection in serpentinite, but in gneiss. So it was another type of test, but we didn't go further. And we have to move money and all the project in another site close to Carfix project. This just like introduction. So this is a very big problem. Of course, we have to find some place not close to the Apennine, not close to the protected area. So there are some. We just try to find the best way, but the big problem is the application in our country. Our country is we have the more project blocked in everywhere. So we are very not so happy for this, but the public acceptance, it's much more problem than feasibility.
Thank you, Chiara. And I don't know if there are other questions in the pipeline, David. Otherwise, I would be happy to ask
No, you
a
can
quick
go
question.
on. If you have another one, please go on.
Yes, thank you. And Chiara, you know that I'm one of the PIs of the DIVE project, or funded by ICT recently. So if the borehole will be open, which type of expense will you envision for CO2 storage in the lower?
Yeah, please. Some tons. Something. Yeah, I know it's a very big problem, but this is also the reason, because after some years that I start and to contact the politics and energy company to try to suggest to make a pilot plant, and I try to suggest an ex-situ mineral sequestration. This is something that for sure we can do, and we have a lot of abandoned mine in Italy. This is also dangerous abandoned mine with asbestos, because take into account that asbestos can be neutralized by CO2 mineral sequestration. And this is something that a W advantage, because in a way you can store CO2, in the other way you can try to find a solution with asbestos, for example, northern Italy first of all, but also Italy in southern Tuscany. There are a lot of abandoned mine. And at the same time, a lot of colleagues from engineers try to figure out other application with alkaline waste. This is another solution for Italy. But this is something that we have to take in mind when we see the IPCC evaluation. If we don't do it, we don't reach 1.5. I will be happy not to do it, CCS, but this is the situation at the moment. Or COVID will stay, will lock our life forever, or this is the situation.
Thank you very much. Are there other questions? Otherwise, I can ask a question to Chiara, which is a question I usually do to the speaker, because to me, all this kind of interesting technology, which we have been facing and overviewed in the last 4 or 5 seminars, they all take into account aspects across the whole essentially cycle, which is a cycle where you take into account the CO2 you want to store in the same amount, in the same times, it's willing to shift across the transition energy, the technology moving from the hydrocarbon production, essentially, so the energy coming from hydrocarbon, and moving slowly to a world where essentially the energy is produced by what we call the renewable. And the renewable, we all very well understand now that requires some storage of different aspects of those energy. Whatever it is, hydrogen in some case, when you want to use hydrogen as a carrier, or whatever you need to store some kind of energy, for what you require some kind of technology like the wind or like the solar, which are not a fully continuous producer of energy across the system. So my question is this one: storing essentially CO2 or hydrogen as a cost. Someone had to pay and to invest in this cost in this system, and in the same time, this implies convincing the industry to be part of this system. So, what is your view? What is your idea on how to build up a real, I would say, business case in which at a certain point the government see an advantage beyond the advantage of the getting a good atmosphere, but as a business advantage? Because this is, I think, part of the problem, which is related to the unknown of this kind of technology from a political point of view.
Yeah, this is a very political problem. The problem come and start, I guess, with the CO2 emission quotas. So if energy company pay only some dollar the quotas for CO2 that they emit, of course, is not push to apply CCS technology. Now, for example, the increase of CO2 quotas, it's increased up to, I think, $30. I don't know. I have an idea, or the last months. And this is something that is comparable to the price that now we think about for each tons sequester. But this is something that depends of all the different variable. For example, most of the money that we spend on CCS is for the transport. So the new trend of CCS is to build up the hub of CCS. So where transport and so CCS emitter and CCS injector is in the same place. And so to avoid the cost, to cut the cost, and to be more trendy for the economic point of view. This is the main reason. Okay, there is the problem of risk of leakage and microseismicity, but this is something that with our knowledge now we can go over. But the big problem for the reason because CCS is not so developed at the moment is the cost. There is no incentive, so the financial incentive of the government from the energy company. So they have to be obliged. Norway, why Norway is the first country that applies CCS since long time? Because they have a tax. They have a very huge tax on CO2. And this has pushed them to make CCS, not because they like CCS, just because money. And money changed the world. And it may also change the world on doing the stuff. So instead of this, we have to incentivize the CCS instead of fossil fuel. This is a big change. And the same of renewable. Renewable, for example, in Italy are very increased with the incentive of the country. Otherwise, it's too expensive. Also low temperature, geothermal energy, everything is expensive at the moment from a technological point of view. Of course, if the market increase, the price of the technology decrease, but at the moment the market is so small that everything is very expensive.
Yeah. Okay. And another comment, I mean, you were just showing in your one of the first slides that unfortunately our country is still very far away. Some of our, we'll say, neighbor from that point of view. I was curious. My curiosity was taken by the fact that apart from Norway, even UK have much more project going on, and why Italy, which technically or potentially would have some very favorable position offshore in typical sedimentary system that have been used to produce gas that can be reused to use as a CO2 storage, as at the moment still none. And I suspect that even the new project that probably Iena will try to start as a pilot in Ravenna is taking probably more time than people were thinking before. So my suspect that we need to do as probably as scientists and as people involved into the geology, a massive effort on explaining to the society what is the role of this technology, what are the limits, but what are also the great opportunity in terms of job, but also in producing a better country from that point of view. And what is your view? Where do you think we should start from that point of view?
Yeah, the problem is it's a political problem, it's a cultural problem. I know very well Ravenna. I don't know if other knows, but I tried to make an hub in Ravenna, and EGG is involved in some aspect on this hub, and it's very usable. It's very convenient place because it's an industrial place. Exactly, it's an hub. Where you can inject in exhausted well CO2. And we try also to make with the ENI a European project, but we arrived in second place and only one was funded. And I think that they will have a very strong opposition also for Ravenna Hub. The only way, I completely agree with you, we have to plan. So we have to have like a planning of energy development in each country. And when we start to make a list and you see that there is no other chance, maybe it's the way to be more communicative with the other. I'm agreeing. I don't like to inject, so I don't like to push natural, but we have to choose, or we keep the temperature below 1.5 degree, or we apply a number of technology that are all the possible technology that we can use at the moment in each country. In it is site-specific choice. No, we can not make solar in Norway that half of the year it's in the dark. But of course, I cannot make an injection in California fault. But of course, we have to test, we have to have an idea, as scientists can help on this, but we have to make a plan, clear. So we have to ask politics to have a plan, a programmation of what we want to have to reach and to meet the Paris Agreement.
Very clear, Chiara. I say that we can close here the conversation. Thank you very much, Chiara, for your talk, for your presentation, which has been very exciting and very interesting. I do remember to all the audience that next week there will be the last talk, and the last talk will be back to CO2 sequestration. Will be Philip Ringrose, which is one of the first that started to experiment in the Sleipner field, and we'll close this series, which has been a very interesting series, a great opportunity for me and for us as a Geological Society of Italy to have a conversation with scientists and people studying across Europe on this subject. So I look forward to see you for the next week. The next week will be at 6 o'clock Rome time. That means 5 o'clock UK. So it will be 1 hour later respect to what has been scheduled so far. And before I do leave, I do thank you very much, Fabio Massimo Petti and Raffaele Viola, for their support with the platform. And therefore, have a nice evening. Thank you very much.
Thank you to all. Ciao, David. Grazie.
No.
Ciao, Chiara.
Grazie, ciao.
Non si sta più registrando.